Okay, recording start already. All right. So everybody get ready, eh? Okay, get ready. We are going to start with 4.2 electromagnetic induction. I know that for STEM 1, okay, we already cover a little bit on the electromagnetic induction, but STEM 2 not yet started lah. Okay, so I start from the beginning for 4.2 electromagnetic induction. Okay, so I hope everybody is ready. Okay, let's start. Okay, so electromagnetic induction. All right, so what is electromagnetic induction? Electromagnetic induction is where, okay, electromagnetic induction is the production of an induced EMF in a conductor when there is relative motion between the conductor and a magnetic field, or when the conductor is in a changing magnetic field. So basically, what electromagnetic induction is about is where, how is it that we can produce electric current, okay, by inducing an EMF. EMF is the source of energy for the current, okay, right? Is the source of energy in the current. So for example, battery have EMF. So the EMF, electromotive force, can drive the charge to go around the complete circuit, right? So then with the charge flowing, then only we can have current. So it's the same thing here. Here is we use electromagnetic induction to induce EMF or to produce and induce EMF, okay, inside a conductor. Okay, so there are two methods in the electromagnetic induction. There are two methods where we can produce induced EMF. So the first one is when there is relative motion between conductor and magnetic field. And then the second is when the conductor is inside a changing magnetic field. Okay, so let's talk about the first one, relative motion between conductor and magnetic field. That means it's like this. Okay, so first we need to understand what does it mean by relative motion. Okay, what does it mean by relative motion? Okay, okay, actually this is inside your paper also, the explanation about the relative motion. Okay, this is inside your paper also, this part. Okay, so it says here, relative motion between two objects is the motion that results in two objects becoming closer to each other or further away from each other. So for example, here we have two objects, A and B. Relative motion occurs between object A and B if object A stationary, object B move towards or away from A. That means like this. Okay, A is not moving, B is moving. B is moving towards or away. So becoming closer or further away from each other. Like that. Okay, A not moving, B moving only. Then we have relative motion. Or B stationary, A move away or towards B. That means B not moving, but A is the one that is moving. If like this, also have relative motion. Okay? Or both objects A and B move with different velocity. That means A and B also move, both moving, but A faster than B or B faster than A, then also will have relative motion. So you can imagine if A and B is moving together, okay, to the right, okay, moving together towards the right. For example, like this, okay, both moving together. Both moving together, but A is faster. So A will slowly catch up to B lah, right? And becoming closer and closer to B. Okay, or if A and B moving together, but B is faster than A, so B will get further and further away from A. So if that is the case, then A and B will get closer or further away from each other lah. Okay, like this, then we say there will be relative motion between the two objects. Okay, get the idea. So no relative motion between object A and B if both object A and B are stationary. Both object A and B move with the same speed in the same direction. Okay, like that, then there will be no relative motion lah. Okay, so I hope everybody can understand what is relative motion. Okay, all right, so let's go back to this definition about electromagnetic induction. Okay, so again, electromagnetic induction is the production of an induced EMF in a conductor when there is relative motion between conductor and magnetic field. So how is it that we can have relative motion between conductor and magnetic field? Okay, let's look at this activity 4.1. This activity 4.1 is where we take this copper rod. You see this copper rod is connected to galvanometer. So when we take the copper rod, we, you see this one here, okay, here and here, this is the magnetomagnet. Okay, this is magnetomagnet, this is also magnetomagnet. So that means in between these two magnets, there is magnetic field. Okay, there are magnetic field between these two magnets. Okay, there are magnetic field between the two magnets. Okay, got magnetic field between the two magnets. So what happened is we take this copper rod, either we move up or we move down the copper rod. Then there will be relative motion. Okay, it's very simple. You see, let's say that this is the magnetomagnet here and here. Okay, so let's say this is north, this is south. So there will be magnetic field north to south, north to south, north to south. Okay, magnetic field north to south. Okay, so let's say that this black color, this is the, oh, sorry. Okay, let's say this is the cross section of the copper rod. Okay, this is the cross section of the copper rod. Okay, so I take this copper rod and then I move up. So you see that the copper rod getting nearer and then getting further away from the magnetic field. Okay, here we call the magnetic field lines as magnetic flux. Okay, magnetic flux. So you see, get nearer and then get further away. Nearer, further away, nearer, further away, nearer, further away. So if like this, then there will be relative motion between the copper rod and the magnetic flux. Then inside the copper rod, okay, that means inside the copper rod, there will be an induced EMF. Okay, an induced EMF will be produced inside the copper rod. And then when you have EMF, electromotive force produced inside the copper rod, then the electromotive force will be able to push the charge to flow inside the copper rod and also along the wire, pass through the galvanometer. So the pointer of the galvanometer will deflect to show the direction of the flow of the charge. Okay, so one thing I need to be clear here is the pointer, the direction of the pointer of galvanometer show the direction of the flow of charge. So when we talk about flow of charge, that means what? That means we are talking about the flow of electron right now, because electron is the one that carry the negative charge and electron is the one that can move. Proton cannot move. Okay, I want to be clear. Proton cannot move. Proton is inside the nucleus, so cannot move. So the one that can move is electron. So let's say that the electron flow in this direction. Okay, pass through the galvanometer, go here. Then electron move in this direction, then the pointer of the galvanometer will deflect that side. Okay, understand? The pointer will go this direction. Okay, it will go like this to show the direction of the flow of charge. Okay, you understand? So because question also can come out and ask you what will be the direction of the galvanometer. So a lot of students, they don't know that the pointer of the galvanometer actually show the direction of charge. Okay, a lot of students, they thought that the pointer of galvanometer show the direction of current. That is incorrect. Okay, why? Because the direction of current is in the opposite direction as the electron, right now. If electron flow this direction, then the direction of the current is in the opposite direction. Okay, so that means the direction of the pointer of galvanometer will show the opposite direction of the current. Okay, get the idea. So this is very important because last time got come out before, okay, got come out before question that asked student what is the direction of the pointer of the galvanometer, or they ask the student to, they draw a galvanometer like this, there is blank. Okay, and then they ask the student to draw the direction of the pointer. The pointer will point in what direction. So I think almost everybody wrong. Okay, almost everybody wrong because almost everybody thought that the pointer of galvanometer show the direction of current. Okay, we use a lot of ammeter, but it's very rare. It's very rare that we use galvanometer. So a lot of people are not familiar with galvanometer. Okay, so now you understand. Okay, that galvanometer pointer point show the direction of the charge flow. Okay, charge flow, which is the flow of electron. All right, so just now we say that okay, when the carbon when the copper rod pass through the pass through the magnetic flux, then there will be relative motion. So in another way, we can say is that when the copper rod or the conductor cut through, okay, cut through the magnetic flux, then there will be relative motion. So that means like this, cut, then got relative motion. Cut, then got relative motion. Cut like this also got relative motion. Like this also got cut. Like this also got cutting. Like this got cutting. So got relative motion. Okay. So how is it that do not have relative motion? That means like this. If move like this, the direction of the motion is parallel to the magnetic flux, then no relative motion. Because you see the distance between the okay, for example, if I put the copper rod here, so the distance is like this. Okay, so that means if the copper rod is here, then you see this is the distance. If the copper rod is here, this is the distance. So you see, if the copper rod move in this direction, then the distance is the same between the copper rod and the magnetic flux, right? Okay, the distance is the same. The distance doesn't change. So that means there will be no relative motion. Okay, no relative motion. So again, the easiest way to see whether got relative motion or not is we see whether the conductor got cut the magnetic flux or not. Okay, whether it got cut the magnetic flux. If got cut, okay, that means move like this, cut, move like this, cut the magnetic flux, then definitely got relative motion. And when got relative motion, inside the copper rod, there will be induced EMF, and then the induced EMF can produce induced current. Okay, can produce induced current. All right. So let's continue. All right. So that means in this activity, when the copper rod move up in the direction A and direction B, then the galvanometer pointer will deflect. If move in the direction of C and D, then the pointer of the galvanometer will not move lah. Okay, it will not move. Okay. So let's continue. If you got question, please ask. Okay, after this, we look at another way. Okay, so you look at here. This one is we use solenoid. Okay, just now is a straight wire, right? On the copper rod, that means straight wire, straight conductor. Now that the conductor is in the shape of a solenoid. Okay, solenoid. So that means the conductor, the wire is coiled up, coil up. And when we push a bar magnet inside through the solenoid, also will induce EMF inside the solenoid, because like this. Okay, so this is the solenoid. Okay, coil of wire. Okay, the solenoid coil of wire. Okay, we connect to galvanometer. So when we take a bar magnet, okay, let's say this is north, this is south. So the bar magnet will produce magnetic flux, okay, or magnetic field. Okay, magnetic flux, magnetic field lines, they are the same thing. Okay, it's just like a magnetic flux is like, it sounds better. Okay, magnetic flux sounds more high class like that. Okay, but they mean the same thing. Okay, so you see this magnetic flux. Okay, so you see the shape of the magnetic flux like this. So that means when you push this bar magnet inside, then this magnetic flux will be cut by the solenoid also, right? That means that this coil of wire, it will cut. Okay, cut the magnetic flux. So that means when you move the bar magnet in or out of the solenoid, then you will have relative motion between the magnetic flux and the solenoid. Then inside the solenoid, you will have induced EMF. Okay, induced EMF produced inside the solenoid, and then the induced EMF will be able to push the charge to flow. And when you have charge flow, then you have electric current. So this electric current we call induced current. Okay, just to be clear, electric current that is produced by induced EMF we call induced current. Okay, like that. The current that is produced by battery, we just say current. Okay, we just say electric current. We don't have special name for that. Okay, so like this also we can produce induced current or produce induced EMF. Okay. Okay, so here, what is it that we want to discuss is that this is actually the same thing. Okay, this shows that this green color is the magnetic flux, And then when we move the wire will cut through the magnetic flux, and then there will be induced EMF is induced inside the wire lah. Okay, EMF induced inside the wire, then you will have induced current. Okay. Okay. However, okay, so you see here, okay, you see here, you compare these two diagrams. You compare these two diagrams. In this diagram, the wire is the one that is moving. Okay, the wire is the one that is moving. Okay, the magnet is not moving. This one, the magnet is the one that is moving. The wire is not moving. So, if we think logically, then we will see that actually the effect is the same lah. Don't care whether the wire is the one that moves or the magnet is the one that moves. The effect is the same. The conductor will cut through the magnetic flux. Right? Okay. It don't care whether the wire is the one that go down or the magnet is the one that go up. That means the wire will cut through the magnetic flux and then will induce EMF lah. Okay, will induce EMF inside the wire. Okay, however, one thing that I want to point out is you look at the direction of the galvanometer. This one, you see the direction of galvanometer is to the left, right? Okay, this one, the direction of galvanometer is to the left. This one, the direction of galvanometer is to the right. Okay, so why like that? The reason is because the direction where the conductor or the direction of the wire cut the magnetic flux is in the opposite direction. You look at this one, the wire go up, right? This one, the wire go up. That means the wire or the conductor cut the magnetic flux upwards. This one, the magnet is the one that move up. If the magnet move up, that means it is the same like the wire is moving down, right? It's the same like the wire is moving down. So that means the direction of cutting is different. This one, the wire cut upwards. This one, the wire cut downwards, right? So when the direction of cutting is different, then the direction of the induced EMF also will be different. Okay, the direction of the induced EMF also will be different, and of course the direction of the charge flow will be different, and the direction of current will be different. So that means the direction of cutting will determine the direction of the induced current. Okay, all right. Okay, so it will be the same with solenoid also. Okay, it will be the same with the solenoid also. If we push the magnet in, compare it with we pull the magnet out, the direction of cutting is different. So that means the direction of the induced EMF also will be different. That means when you push in, the direction of the induced current is one direction. When you pull out, the direction of the induced current will be in the opposite direction. So different direction of cutting, then different direction of induced EMF. Okay, Okay, now that we already learned how to produce the induced EMF, okay, you see from the beginning until now, what is it that we learned is, okay, how is it that we can produce induced EMF? Okay, so we learned that, okay, when we take the conductor and if the conductor cut the magnetic flux, then we'll produce induced EMF. And we also learned that if we cut in different direction, then the direction of the induced EMF also will be different. Okay, so now that we already learned how to produce the induced EMF, we want to learn what are the factors. Okay, what are the factors that affect the magnitude of the induced EMF? That means what are the factors that can make the induced EMF bigger or smaller? This is very important because induced EMF produce the induced current, right? Not? So that means if we can have a bigger EMF, then we can have a stronger current, right? So we want to learn how is it that we can produce a stronger EMF, okay? How to make the EMF bigger. Okay, so factors affecting the magnitude of the induced EMF. Okay, so here you see this activity, the speed of magnet. This activity is where we push the bar magnet in and out of the pull out of the solenoid. Okay. Okay, so you see there are two speed of magnet, slow or fast, and then number of turn of solenoid 400 or 800. Okay, so the result will be if we move the magnet slow, then the reading of the galvanometer will be low. Okay, okay, the reading will be low. When you move fast, then it will be higher. Okay, that means if you move the magnet faster, or if the speed of cutting the magnetic flux is higher, that means you cut the magnetic flux faster, then you have stronger EMF. Okay, you have stronger induced EMF. Okay, so that means if you want to produce a stronger EMF or to produce a stronger current, then you cut the magnetic flux with a higher speed. Then you can produce a stronger EMF. Okay, next is you see this number of turn of solenoid, 400 and 800. Okay, so this 800, if you compare the 800 turn and the 400 turn, you will see that the 400 turn, you will see that the 800 turn will be, you will get a higher reading. That means if more number of turn, then you also produce stronger EMF. Okay, that means this reading will be higher compared to this one. Okay, this one is this and this one is about the same. Okay, but this is higher than this one. This one is higher than this one. Okay, so you can get a stronger EMF if you move the magnet slow, but you have more turn. Okay, more number of coil, then you can also produce a stronger EMF. The logic is very simple. Okay, the logic is very simple. You see, the solenoid is consists of coils, many turn, right? Okay, turn. Okay, so you see, if when you push the magnet in, the coil, every single coil will cut through the magnet. So that means every single coil will have induced EMF inside each single coil. That means every coil will produce induced EMF. And all of these coils, they are connected in series, right? They are all connected in series because they are all one single wire. One long wire, you wound, become many coil. So that means each and every coil are connected in series. So you know lah, if you take one battery, if you take two battery, 1.5 volt, 1.5 volt, you connect in series, then total you will have 3 volt, right? 1.5 volt plus 1.5 volt, then you get 3 volt. So imagine, let's say that every single coil can produce 0.1 volt lah, for example lah. Okay, when the coil cut the magnetic flux, every coil produce 0.1 volt. Let's say lah, for example lah. Then if you have 10 coil, then all add together you get 1 volt. If you have 20 coil, then you get 2 volt. 30 coil, then you get 30 volt lah, like that. Okay, get the idea. Okay, it's very simple. So that means here we learn two methods. Okay, two ways to increase the EMF. Okay, two ways to increase the EMF. So for straight wire and magnet, the two ways are, if the speed of relative motion increase, that means you cut faster, then the strength, then you get the induced EMF will increase lah. Okay, induced EMF will increase when the speed of relative motion increase. That means you cut faster. Second is if you use a stronger magnet lah. Okay, if you use a stronger magnet, also you can produce a stronger EMF. Okay, this is the two basic. These are the two basic factors that can affect the magnitude of the induced current. One is you cut faster. Second is you use stronger magnet. Okay. Now for solenoid and magnet, also same thing. First is speed of relative motion increase. That means you cut faster. Second is you see strength of magnetic field increase. That means you use stronger magnet. But for solenoid, you have another one. That means number of turn of solenoid increase. That means you increase number of turn lah. Okay. So for solenoid, there are three methods lah that we can produce a stronger EMF. But this one, the number of turn actually have nothing to do with electromagnet lah. Okay, have nothing to do with electromagnetic induction. It's just that we use the concept of like series circuit lah. You connect many coil in series, then all the coil join together, add together, then you get a higher EMF lah. So actually that has nothing to do with electromagnetic induction lah. Okay, but the actual concept to increase the strength of the induced EMF is only two lah. That means you have higher relative motion. You move faster, cut faster, and then second is you use a stronger magnetic field. Stronger magnetic field, that means the permanent magnet, that means the bar magnet that you use is stronger. So how to get a stronger permanent magnet? One way is you combine two bar magnet together lah. Okay, you combine two bar magnet together, then you can get a stronger magnetic field. Okay, that means you use multiple magnet at the same time. Okay, together like that. Okay, so this factor that can affect the magnitude of the induced EMF is explained by Faraday law. Okay, Faraday law. Faraday law states that magnitude of induced EMF is directly proportional to the rate of cutting of magnetic flux. Okay, rate of cutting of magnetic flux, that means is like how fast you are cutting the magnetic flux. Okay, how fast you are cutting the magnetic flux. Okay, so you see it says here, magnitude of induced EMF directly proportional with rate of cutting of magnetic flux. So basically, this explains these two things. The Faraday law talk about these two. If you cut faster, then that means rate of cutting of magnetic flux will be higher, right? Now you cut very fast, you move fast. Okay. Second is when you use stronger magnetic field, okay, what is the characteristic of stronger magnetic field? When the magnetic field, if the bar magnet can produce stronger magnetic field, that means that the bar magnet will have, that means the density of the magnetic flux will be higher. That means like this. Okay, we compare two bar magnet, okay. Let's say this one and this one. Okay, this one knob, this one also knob lah. Okay, so you see this one is like this. Compare with this one. So this one, you see the density of the magnetic flux is higher than this one. You see more magnetic flux, right or not? This one, the number of magnetic flux is less, or the number of the magnetic field lines. Okay, one have more magnetic field lines, one have less magnetic field lines. So the one with more magnetic field lines, that means the density of the magnetic flux is higher. This one, the density of magnetic flux is lower. So the one with higher density of magnetic flux, that means the magnet is stronger. Okay, understand? This one is stronger than this one. So if you have more magnetic flux, that means when you cut, you just move the conductor one time, pass through one time, you can cut many magnetic flux at the same time, right or not? This one, you move one time, the number of magnetic flux that you cut through is less. So that means if you can cut through many magnetic flux at the same time, this will also means the rate of relative motion is also higher. Get the idea or not? Okay. The rate of cutting of magnetic flux also high. Okay. The rate of cutting of magnetic flux is also high if you use a stronger magnet. Understand or not? Because you can cut many magnetic flux at the same time. That means you can cut the magnetic flux faster. Get the idea? So both have the, so that means the Faraday law, when it says that magnitude of induced EMF directly proportional with rate of cutting of magnetic flux, this is talking about these two, both of these at the same time. Okay, because if you cut with a higher speed, then that means you have a higher rate of cutting. If the strength of magnetic field increase, that means you can cut many magnetic flux at the same time. That means you also have high rate of cutting. Okay, so that means you can have a stronger EMF lah. Okay, magnitude of induced EMF will be higher. Get the idea? So this is very important. Faraday's law. Okay, Faraday law talk about how is it that we can produce a stronger induced EMF. Okay, that is what Faraday law is talking about. Okay, so until here, any problem? Anybody have any question or maybe cannot hear clearly? Or everybody go to sleep already? Okay, thank you very much for responding. Okay, thank you very much for responding. All right. Okay, so can continue, Okay, let's continue. So until here, what we learned is how to produce the induced EMF and we learned that, when we cut the magnetic flux in opposite direction, then the direction will also be different. And then the third thing that we learned is how to make the induced EMF stronger. Okay, until now, this is the three things that we learned. Okay, so how is it that we can make the magnetic flux, how is it that we can make the induced EMF stronger? It can be explained in Faraday's law. Okay, Faraday's law. Okay, next is we want to talk about the direction of induced current in a straight wire and solenoid. Okay, so previously we already learned that when we cut in different direction, then the direction of the induced current is different. Okay, when we cut in the different direction, then the direction of induced current will be different. Okay, so what is it that we want to learn here is how is it that we know, or when we cut in this direction, what is the direction of the induced current? Okay, how do we know the direction of the induced current if we cut in this direction? Okay, so that is what we want to learn here lah, to find out the direction of induced current. Okay, to find out the direction of the induced current. Okay, so in this activity 4.12, to study the direction of induced current in a straight wire. Okay, so first is we test with a dry cell to see what is the direction of the what will be the direction of the pointer of the galvanometer. Okay, that is the purpose of why we connect to the dry cell first, because for the dry cell we already know that which side is positive, which side is negative, right? Not we already know which is positive, which is negative. So we want to find out what will be the direction when we connect, when the current flow in this direction, what will be the direction of the galvanometer. Okay, so after that we cut the magnetic flux by using a conductor, and then we compare this direction of the galvanometer with the direction from the dry cell. Then we can see that when we move this direction, then that means which side will be the positive, which side will be the negative. Okay, get the idea or not? So for example, okay, this is let's say this is positive, this is negative. So the current will flow this direction from positive to negative, right? If like this, that means the direction of the pointer will point this direction. Remember, just now we got say that the direction of the pointer show the flow, so the direction of flow of the charge. So the direction of flow of charge is the direction of flow of the electron. Direction of flow of electron is in the opposite direction of the current. Okay, so if this is positive, this is negative, so that means the current will flow this direction. So that means the pointer will point to the left side. So let's say that we move this XY, this conductor upwards in the A direction. Okay, in the A direction. So what is it that we find out is, okay, what is it that we find out is that, the pointer point this direction. Okay, when we move up, we see that the pointer go to the left. If the pointer go to the left, so that means the direction of the electron, that means the electron flow in this direction. Okay, the electron flow in this direction. If the electron flow in this direction, that means what? That means the current is in the opposite direction lah. That means the current flow this direction. Right or not? That means the current flow like this. If the current flow in this direction, that means that if we compare this XY to the positive negative of the dry cell, then we can see that this must be positive, this must be negative lah. This is the positive terminal, this is the negative terminal. Then the current can flow like this in this direction. You see or not? Okay, and then after that, we move this conductor downward in the B direction, downward. And then we find that the galvanometer will point in the opposite direction. So when point in opposite direction, that means this positive, negative is in the opposite direction already. That means this Y become positive, this X become negative. Okay, can see or not? This Y become positive, this X become negative. So, so now we know that which direction that we move can cause the EMF to be in which direction. Okay, can see. Okay. So the conclusion is here lah. So this is the magnetic field lines from north to south. When this is the direction of motion, then the direction of induced current is in this direction. When you move the, okay, this one is if you move the magnet down, that means you don't move the wire, but you move the magnet down. So it will be the same like the wire move upward, right or not? So that means you see the direction of the induced current also same. Okay, this is move the wire. This is move the magnet. Okay, wire don't move, but move the magnet. But both also have the same effect lah, where the wire cut the magnetic flux. Okay? Okay. Okay, now comes the very important part. This part is very important. Draw the resultant magnetic field with direction of force and direction of induced current. This one we will study, we will look at why is it that the direction of the current will be in such direction. Okay, this part is very important. Okay, you see, wait, sorry, wait, got something, wait, wait, okay, sorry, okay, so this part is very important, okay, you see, seriously, very important, okay. Okay, let's say that we have this is the magnetron magnet, okay, this is the magnetron magnet. Okay, so okay, I follow this one, okay, I follow this one, so this side is north, this side is south, and then we have the magnetic field lines. North to south. Okay, magnetic field lines north to south. And then this is the conductor, okay, the cross section of the conductor. So you see this cross section of the conductor, no current, it's not moving, so there's no current. Okay, now you see when we move the conductor into, when we move the conductor into the magnetic field, that means we cut through the magnetic field. Okay, cut through the magnetic field. After cut through the magnetic field, inside the conductor will have induced EMF. And then the induced EMF will produce induced current, right now. If you have induced current, that means you have electrical energy, right? You have electrical energy. Okay, now I need you to think, where do the electrical energy come from? Where do the electrical energy come from? Last time we got learned about principle of conservation of energy, right now. Remember principle of conservation of energy. This is very important. This part is very, very important. Okay. Principle of conservation of energy says what? Energy cannot be created or destroyed. It can only be converted from one form to another. Right now. That means if you want to have electrical energy, then you must convert other kind of electrical, you have to convert other kind of energy into the electrical energy, right? You have to supply energy in order to get energy. So you cannot create energy from nothing. Okay, you cannot create energy from nothing. So for example, last time in when you learn about in lower form science, you got learn that you got learn about simple generator. So when you rotate the generator, you will get electrical energy. So you can see that the generator convert kinetic energy. When you rotate, you rotate the generator, you supply kinetic energy to the generator, and then the generator convert that kinetic energy into electrical energy. Okay, very simple. Convert into electrical energy. Okay, so but maybe you will think, how is it that it convert kinetic energy into electrical energy? I'm still rotating the generator. The generator is still rotating. That means it still got kinetic energy, but at the same time also have electrical energy. If convert the kinetic energy into electrical energy, then there should be no more kinetic energy, right? Okay, all right. Okay, sure. Tired. Okay, so later make sure you watch the what, the recording lah. Wait, okay, Tai say his computer got problem. Okay, so let's continue. So we want to supply energy, then only we can get electrical energy. Okay, so of course it's the same thing here. When we push the when we push the wire in and cut the magnetic flux, we give the wire kinetic energy. Okay, we give the wire kinetic energy. Okay. But the thing is, the kinetic energy that you supply, okay, the amount of energy that you supply, it must be more than the kinetic energy that is moving the conductor. Okay, why? You see, okay, you see, okay, here we have, okay, we have, okay, these two, they are magnet, okay, north south. Okay, these two, they are not magnet. So let's say this is wood. Two pieces of wood, two pieces of wood. And we take the conductor and we push the conductor in between the two wood. Inside got electrical energy or not? Can induce electrical current? Of course not lah, right? Of course not. No electric current. Okay, now, so let's say that we push this wood inside. Let's say the amount of energy that we give is, let's say, 100 joule. We give 100 joule to this conductor, and the conductor pass through the wood. So the conductor pass through the wood, let's say with the, let's say we are not going to calculate exactly, just example. Let's say that, okay, I give the conductor 100 joule of kinetic energy, and the conductor can pass through the wood with a velocity of 10 meters per second, for example. Okay, so the velocity of the conductor is 10 meters per second. Okay, now, when I do the same thing, okay, to this conductor, I also give 100 joule to push the conductor pass through the between the two magnets. The conductor will cut through the magnetic flux. Will the conductor have the same velocity or not? Is the conductor going to have 10 meters per second velocity also? The answer is no. The velocity of the conductor will not be 10 meters per second, same as this one. It will not be 10 meters per second. The velocity will be slower than the 10 meters per second. So let's say that the velocity is only, the velocity is only 5 meters per second. So why is it that this one I push 100 joule kinetic energy, it can move 10 meters per second, but this one 100 joule I push, this only move with 5 meters per second? The reason is because out of this 100 joule that I give, only a part of the 100 joule become the kinetic energy. Another part, the rest of the energy turn into electrical energy inside the conductor. Understand now? That is why the velocity will be slower, because only a part of the kinetic, so only a part of the 100 joule turn into kinetic energy. The rest turn into electrical energy. Get the idea? Okay, so you see, you push with your hand. Let's say you push with your hand. What is it that you will feel What is the different feeling when you push this through and when you push this through here? You see, you push with 100 joule, this one moves slower. This one, you push with 100 joule, it can move faster. What is it that you feel actually? What is it that you feel is an opposing force? You will feel an opposing force make the movement of the conductor slower when you pass through the magnetic flux. That means this one, when you push the conductor pass through, you don't feel something push back. But this one, when you push the conductor pass through, you feel something push back. There's an opposing force. So that opposing force makes the velocity become slower. Or in other words, you will feel like it is more difficult to push the conductor pass through the magnetic flux compared to this one, pass through the wood. Okay, you feel more difficult to push the conductor pass through the magnetic flux. Okay, so how is it that this force can be produced? This opposing force can be produced by the magnetic flux. Why is it that you got this force? Okay, so this is what we want to learn. This is a part of the thing that we want to learn here. How is it that this opposing force can be produced? Okay, you see, when we push, you see, back to here, when we push the conductor pass through the magnetic flux or cut the magnetic flux, okay, cut the magnetic flux, what happens is an induced EMF will be produced in the conductor right now. There will be an induced EMF. So this induced EMF will produce induced current right now. Okay, got induced current. So the induced current, you see, if got current, that means the current will produce magnetic field, right? Okay, when got current will produce magnetic field. So that means what happened is around this conductor, inside the magnetic field got magnetic field, because this conductor got electric current. Okay, because this conductor got electric current, induced electric current, induced current. So the induced current produce magnetic field. You see or not? Produce magnetic field. Okay. And then you see here, just now, we say that when we push the conductor in, we feel an opposing force, right? This opposing force must have come from the resultant magnetic field between the magnetic field that is produced by the current combined with the magnetic field from the permanent magnet, from the magnetomagnet. That means the opposing force that we feel just now, when we want to push in, we feel difficult to push in. We feel an opposing force. So where do this opposing force come from? This opposing force must have come from the combined magnetic field of the magnetic field that is produced by the current and the magnetic field produced by the magnetic field from the permanent magnet. So if this is the direction of the opposing force, that means the magnetic field, the combined magnetic field or the resultant magnetic field must look like this. It must be like this. You see, here is stronger magnetic field, here weaker magnetic field, so can produce a force in this direction. The stronger magnetic field push towards the weaker magnetic field. That means produce a catapult force in this direction. Can see or not? Okay, produce a catapult force in this direction. So this is how the opposing force is produced. And if the magnetic field is in this direction, if the magnetic field is in this direction, if the magnetic field can produce an opposing force in this direction, that means this direction of the magnetic field, this direction, the direction of the magnetic field that is produced by the induced current must be in this direction. The direction of the magnetic field, I repeat, the direction of the magnetic field that is produced by the current must be in this direction, anti-clockwise. Then only it can make the magnetic field from the permanent magnet bend like this. Okay? To produce an opposing force like this. And then if the magnetic field that is produced by the current is anti-clockwise from right-hand grip rule, we can find that the direction of the induced current must be outwards. That means going from inside out, okay, towards us, out of the plane of the paper. Understand? Must be in this direction, going out. So that means from this method, method of deduction, we can find out the direction of the induced current. You see or not? Okay, through this method, we find out the direction of induced current. Okay, one more time. When we want to push in, we feel an opposing force. How is it that this opposing force can be produced? The resultant magnetic field from the current and from the permanent magnet must look like this. If we look like this, that means the direction of the magnetic field of the current must be anti-clockwise. And if it is anti-clockwise, then the direction of current must be outward, coming out from the plane of paper. Okay? So this is how we deduce the direction of the induced current. Okay, now, until here, any question? Can understand or not? Any question? Okay, no question. Thank you very much for responding. Thank you very much for responding. Okay, now. Okay, now. Okay, now you see the relationship between the magnetic flux. Okay, this is the direction of the magnetic flux of the permanent magnet. This is the direction of the induced current. Okay, perpendicular. This induced current, this is the magnetic flux. And this is the direction of pushing the conductor. Direction of the force. So you see, push upwards. This is the direction of the force, push upwards. This is the direction of the opposing force. Okay, opposing force. This is the direction where we push the wire in. So you see that all these three are perpendicular to each other. Direction of the force, perpendicular with direction of the magnetic field. Magnetic field, direction of magnetic field perpendicular with the direction of current. Direction of current perpendicular with my with the force. Okay, direction of the current perpendicular with the direction of the force. Okay, so that means from this diagram, from this relationship, when the direction of the, if we can find out the direction of two of this variable, then that means we can find out the direction of the third thing. You see, for example, if we know the direction of the magnetic field, we know the direction of current, we can find out the direction of the force. If we know the direction of force, direction of current, we can find out the direction of the magnetic field, and so on, like that. So this diagram, the relationship between the direction of these three things, we represent by using our right hand. Okay, by using our right hand, okay, by using our right hand to represent the three variable. Okay, to represent the three variable. So you can see that, okay, this is the direction of the force. This is the direction of the magnetic field. This is the direction of the induced current. Okay, all three, they are perpendicular to each other. So this is the same as this. Okay, they are the same as this. Okay, or maybe this one I should draw. Okay, I draw this here. Okay, like this. Then you see this one. This is the current. This and this. They are the same. Okay, they are the same. So this is the force. This is the magnetic field. This is the current. Okay, it's the same. Okay, all right. So by using the this is what we call the Fleming right hand rule. Okay, Fleming right hand rule. So now we have two Fleming hand rule. One is Fleming left hand rule. One is Fleming right hand rule. So Fleming right hand rule. Okay, what we are seeing here, Fleming right hand rule is used to find out. Is used where there is no current, you produce your own current. That means by using electromagnetic induction, you produce the current, then you use Fleming right hand rule. Fleming left hand rule is where you have a power source, you have a battery, you have power supply that supplying the electric current. And then the electric current produce the force. That you use Fleming left hand rule. So it's very simple. Fleming left hand rule already got current. Current produce force. Fleming right hand rule, no current. You use the force to produce the current. That is Fleming right hand rule. Okay, so I hope that you can differentiate Fleming left hand rule and Fleming right hand rule. Okay, all right. So let's try some example. You see, this is blank. So actually, we need to draw the example. Okay, so I draw the example. Okay, so first is this is the magnet like this. This is the conductor. Conductor is in this direction. This is north. This is south. Okay, so find out the direction of the induced current. What is the direction of the induced current? Find the direction of induced current. Okay, and then the next one is like this. Okay, these two, this is the magnet. This one is the magnet. This is the conductor. Okay, and this is the direction of the force is here. Okay, this is the direction of the force, and this is the direction of the induced current. So find out the polarity of the magnet. Find the pole of the magnet. Okay. Okay, try it now. Okay, copy down this example and you try to find out the direction of the induced current and direction and find the pole of the magnet by using Fleming right hand rule. Okay, done. Okay, so let's okay, anybody can tell me this one, the first one, the direction of induced current. Is it out of the paper or go into the paper? Inward, very good. Ananti, very good. You are correct. Okay, very good. So this one, the the direction of the induced current is into the paper. Wait, wait. Okay, so okay, very good, inward. Okay, so next is the pole of the magnet. Okay, what are the pole? This one, let's say, okay, this is magnet X. This is magnet Y. So X and Y. Which one is north? Which one is south? X south, Y north. Okay, unfortunately, is incorrect. Unfortunately, is incorrect. Okay, X is actually north, Y is south. Okay, uh, you see, okay, you try again. First, you set the direction of current first. Direction of current is downward. Okay, direction of current is downward. And then you turn so that the direction of the force is to the left. And then you can see that the direction of the magnetic field is inwards, going into the paper. Inward, inward. So if the direction of magnetic field is inwards, so that means X must be north and then going in to the south. That means go to the Y. Okay, can understand? Any question? Any problem? Lo jamming? No, I don't understand it. Okay, so let's see. How? Okay, then let me draw. Okay, so your hand should look like this. Okay, this is your thumb, and then this is your finger. Okay, and then this finger. Uh, wait, like this. That means this finger point downward. So this is current. This is force. This is the direction of the magnetic field. Okay, this is your Fleming right hand. Okay or not? This is your thumb, thumb. This is your first finger. This is your middle finger. Middle finger is the current. Okay, so if the direction of magnetic field is this direction going inwards, so that means the magnetic field is like this from north to south. Okay, the magnetic field is from north to south. Okay, the magnetic field point like this, so that means this one is north, this one is south. The magnetic field go from north to south. Okay, all right. Okay, All right, so next is the, okay, now we already learned how to find out the direction of the induced current for straight wire. What we learned is straight wire. Okay, the wire that is straight. How to find out the direction of the induced current. Okay, next is you want to find out the direction of induced current in a solenoid. Okay, so we use the same concept. What is the same concept? That means when we push the magnet in, the solenoid will cut the magnetic flux. So when it cut the magnetic flux, that means the coil of the solenoid will have induced EMF. The induced EMF will produce induced current, and the induced current will produce magnetic field. So the magnetic field from the induced current will interact with the magnetic field from the permanent magnet. So they will produce a repulsive force. It will repel. Okay, that means the magnetic field from the induced current, it will go against the movement, go against the magnetic field. Okay, go against the movement that want to produce the induced current. Get the idea? Same like this one. You see, we push in, so this force produce the induced current. So the magnetic field of the induced current produce an opposing force to push back. So same thing with solenoid also. When you want to push the solenoid in, the magnetic field that is produced will go against the motion. When you want to pull out, the magnetic field will go against the motion. Want to pull in. Okay? So that means what? How is it that it can oppose? How is it can oppose the motion? That means this magnetic field from the solenoid must produce. You see here, if this is north, how is it that it can repel? This side must be north. This side must be south. So north and north will repel. Okay? So from right-hand grip rule for solenoid, right-hand grip rule for solenoid, we can find out that if this is north, that means the direction of current must be like this. Okay, right-hand grip rule for solenoid, like this. This is your thumb. This is your right-hand grip rule. So this is the north. This is the direction of the current. Okay. So like this. So we can find out that the direction of current is like this. And if the direction of current is like this, that means the pointer of the galvanometer must be like this. If this one we pull out, then the opposing force is attract, want to pull in the magnet. So that means this one is south, then this side must be north. Also, you see in the diagram, this one will change. This one becomes south. Okay, if you want to pull out, this one must be north also. Okay, or okay, I think I changed that. or if okay, let's say I change side and north change to south. Okay, but I push in also. So that means it must be opposing force. Must be opposing force. So this side must be south also. South and south, they will oppose to each other. This side is north. If like that, again from right hand grip rule for solenoid. So your right hand grip rule for solenoid should look like this. Okay, this is your right hand grip rule for solenoid. So this is north, and then this is your direction of current. Okay, this is your direction of current. So this is the direction of current in the solenoid. So if this is the direction of current, then the galvanometer should point in this direction. And see or not? Okay. So the concept is the same. Don't care whether it is straight wire or solenoid, the concept is the same. That means when you want to produce electric current or electrical energy, you need to give some part of the energy will be converted in some part of the energy that you use to move the to produce the motion that produce the electrical energy will be converted into electrical energy. So you will feel an opposing force. Okay, so that you need to produce extra energy to overcome that opposing force. Then that extra energy that you use to overcome the opposing force will convert into electrical energy. Okay, that is where the electrical energy comes from, from a part of the force that you use to move the to produce the relative motion or to produce the cutting effect, okay, to produce the cutting. Okay, all right. Okay, so this is the discussion. Okay, you see, magnet push towards solenoid, then this side will be north. You see or not? That means the induced current in the solenoid will make this side of the solenoid become north. So north and north it will repel. So the induced current in this direction, you see, induced current in this direction, the pointer will point in the opposite direction. Okay. When you change side, north south change, then the direction of the current also change. Okay, this one south south, it will repel. Okay, this one north, you pull out, then this side becomes south because want to oppose the motion. So in the it will so it will want to pull in. You want to move out, it will pull you in. It will oppose the motion. Okay, go against the motion, oppose the motion. So this side becomes south, this side becomes north. Okay, so this will be the direction of the current. This one also same. You change north and south, change, pull out. This one become north to pull in. Okay, like that. So through this concept, we can find out the direction of the induced current. Okay. All right. So this concept about how is it that we can find out the direction of induced current is explained in Lenz's law. Lenz's law states that the induced current always flow in the direction that opposes the change of magnetic flux that causes it. That means the direction of the induced current, okay, the direction of the induced current will always produce a magnetic effect that oppose the change of the magnetic flux that produce the induced current in the first place. Okay, get the idea? It is the same like how you say it is as though the magnetic flux don't want to have changes. So if you disturb the magnetic flux will produce the induced current that produce magnetic field that oppose the changes. Okay, that means you want to make the changes go back to normal. Okay, you change it, you want to go back to the original situation. So how it produce a current that is in the opposite direction. Sorry, not in opposite direction. It produce a current that can produce magnetic field that can make the changes go back to normal, okay, to oppose the change of magnetic flux. Okay, like that. For example, okay, for example, this one. At first, the magnetic flux is straight line, right? Not to south, straight line. But when you push in, you cause changes to the magnetic flux. That means you disturb the magnetic flux. So the effect of the result of disturbing the magnetic flux is it produce an induced current, produce magnetic field that oppose your motion, oppose the movement that disturb the magnetic flux. Understand that? So it produce an opposing force. Okay, get the idea. So you see, every time you disturb, every time you cut the magnetic flux to produce induced current, it will always produce a magnetic effect that opposes the motion. You want to push in, it will push back out. Same with the solenoid also. Same with the solenoid. You want to push in, you push back out. You want to pull out, okay, push in, push back out. No. You want to pull out, it will pull you back in. Okay, pull back in, oppose. You see, north south. Okay, so based on this concept, where it will always oppose your motion, then we use that idea, we use this concept to find out the direction of the induced current. Okay, so that is what Lenz's law is talking about. Okay, Lenz's law explain the repulsive force experience when when producing induced current. Disagree with principle of conservation of energy, where work done to overcome the opposing force is converted into electrical energy. Okay, so in electromagnetic induction, there are two important physics laws: Faraday law and Lenz's law. Faraday law talk about how to make the induced EMF stronger. Lenz's law talk about how to find out the direction of the induced current. Okay, so this is the two important physics law in electromagnetic induction. All right. Okay, so until here, any question? Okay, anybody have any question? Okay, thank you very much. Okay, thank you very much for responding. Okay, so let's continue. We don't want to waste time. Okay, and it's the recording is running also. At first, I want to give like a little bit of time resting, but if a little bit of time resting, then the recording will keep on running and then there's nothing going on. Okay, so we continue. If you want to rest a bit, you can like, okay, while listening, okay, while listening, you can like close your eye a bit or, okay, or get something to drink or get something to eat. Okay, like that. Okay, but we continue on. Okay, I want to finish off this topic lah. Okay, this topic today. All right. All right. So continue. Okay. Now that we already learned how to produce the induced current. Okay. We know how to produce induced current. We know how to find out the direction of the induced current. Now we want to learn how to use that knowledge, how to use these two knowledge to generate electricity. That means we want to design a machine that can generate electricity. Okay, so we call that machine a generator. Okay, we call that machine a generator. So the first is we want to learn about is direct current generator. So like what the name say, direct current generator is a generator that produce direct current. Okay, it's a generator that produce direct current. All right. So let's look at this diagram. Okay, so you see, this structure is exactly the same as direct current motor. It's exactly the same as DC motor. Exactly the same, 100% the same, except, sorry, not 100%, except this one. In direct current motor, this one, all you need to do is you put power supply or you put battery here. You supply the current to the coil, and then the coil will produce catapult force and then can cause the coil to rotate. So you have direct current motor. Okay, here in direct current generator, you see the split ring commutator and the carbon brush is the same, exactly the same as the direct current of DC motor, direct current motor. But this one, you don't have power supply because what you do is you rotate the coil. Okay, you rotate the coil and electric current will be produced because the coil, this side, the AB and the CD, this side will move up, this side will move down, and then it will cut the magnetic flux. When it cut the magnetic flux, induced current will be produced inside the coil. Okay, you will have induced current. Okay, so the induced current will flow through the resistor here lah. Okay, so let's look at how it works. Okay, let's look at how it works. Okay, so look at this one, process one. Look at this process one. Okay, I make this bigger a bit. Okay, so let's say that wait a minute. Let me make this bigger a bit. Hey, wait. Not enough space. Okay, so look at this process one. Okay, so let's say that, okay, let's say that this is, you see, the coil is vertical like this. So let's say that this is A, B, C, D lah, down here. Okay, this is A, B, C, D. Okay, so when you rotate in this direction, okay, rotate in this direction like this, you see the coil AB and the CD got cut the magnetic flux or not? There is no cutting in magnetic flux, no cutting in magnetic flux. Okay, why no cutting in magnetic flux? Okay, let me draw. You see, let's say that, okay, this is the magnet here and here. Okay, and you see, okay, let's say that, okay, here the cross section of the coil is here and here. This is the cross section of the coil. This is AB at the top here, AB. This one is CD at the bottom here. Okay, this one, and this one. So you see, when it rotates, this coil is moving in this direction. This coil is moving in this direction, right now. So if it's moving like this, okay, this is north, this is south. Okay, this is N. U is Utara, north. Okay, N like this. So when it's moving like this, you see the direction of the motion of the coil is parallel to the magnetic flux. Okay, the direction of the motion of the coil is parallel to the magnetic flux. So that means there is no cutting. There is no cutting of the magnetic flux. So if no cutting of magnetic flux, then there will be no induced current. Okay, you don't have induced current. You see that? So that means here, when in this position, there will be no induced current. So in this position is here. In this graph is here. No voltage. The voltage is 0. Okay, the EMF that is produced is 0. Okay. Okay. Next, when it continue to rotate until the process 2, so you see here become, this is A, B, C, D. Just now is vertical, so now it rotate until here. So this side is A, B, C, D like this. So when it rotate until become like this, so you see this side, the direction of motion is downward. This side, the direction of motion is upward. So if like this one cut downward, this side cut upwards. Okay, so by using Fleming right-hand rule, we can find out the direction of the induced current. Okay, so north to south, the direction of magnetic field, north to south. The direction of cutting is downward. So the direction of the current is this direction. So the current flow in this direction. Go to this side of the commutator. Go here, here, and go in this direction. And you see the current is in this direction. Actually, this diagram is wrong. This diagram, the pointer of the galvanometer should be this side. Okay, the pointer of the galvanometer should be this side. Okay, and then the current will flow in this direction. Flow like this to the carbon brush, to the commutator, and then go here, in this direction like this. Okay, so the current flow in this direction. Okay, you can see, okay, the current flow in this direction. So here, the direction of cutting is 90 degrees. That means That means the coil move until here. A, B, C, D. Okay, that means this is A, B, this is C, D here. So the direction of cutting is like this. You see this one going down, this one going up. So 90 degree. The direction of cutting is 90 degree to the magnetic flux. Okay, north to south. Magnetic flux is north to south. This is the direction of the magnetic flux. Like this, north to south. So you see the direction of the cutting is 90 degree. 90 degree, you see? So when the direction of cutting is 90 degree, the EMF that can be produced is maximum. So that means it's here. Okay, can see or not? Okay, that means it's here at the maximum EMF that can be produced. Okay. Okay, now go to process 3. Continue to rotate. Now the AB is here already. AB is here. This one is CD. So you see when move like this, the direction of movement is like this. The direction of movement of the coil is this direction. That means the direction of movement of the coil is parallel with the magnetic flux. You see or not? Parallel with the direction of the magnetic flux. So that means no cutting. Okay, when no cutting, that means no EMF lah. Okay, do not have induced EMF. So here during process 3, the induced EMF go down until here. Okay, 0. And then continue to process 4. Okay, when go to process 4. Okay, so that means now AB is here. Here is CD. Okay, so the direction of cutting, this one AB going up, this one CD going down. Okay, so you see, let's look at AB, the direction of the induced current, AB. Okay, so the direction of magnetic field by using Fleming right-hand rule, Fleming right-hand rule, north to south. Okay, north go to south, direction of magnetic field, direction of force upward. So the direction of the induced current is this direction. This direction. So the induced current is in this direction. Go here, go here, 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 and this direction. So again, here got problem. The direction of the galvanometer should point here. Okay. And then the current flow this direction. Here from the carbon brush to the commutator, and then go into the coil in this direction. Okay, so you see this direction of the induced current and the direction of the induced current here is the same direction, you see or not? This one is to the left side. This one also to the left side. That means the direction of induced current is the same. So since the direction of induced current is the same, then from the graph, that means on the graph, the induced EMF is going up until here. You see in the same direction. So this is process 1, process 2, process 3, process 4. Okay, process 1, process 2, process 3, process 4. Okay, if continue to rotate, then it will go back to process 1 here. Okay, so if we look at the angle of rotation, this is, let's say this is 0, starting. If starting here, process 1 starting, this one is 0 degree. Then rotate until here, it will be 90 degree already, right? Rotate until here, it will be 180 degree. And then rotate until here, it will be 270 degree. Continue to rotate back to process 1, it will be 360 degree. You see? So if we label the graph with angle, let's say this one is an angle of rotation, then it will be 0 degree, 90 degree, 180 degree, 270 degree, and 360 degree. You see or not? So this 360 degree here is the same as process 1. Okay, so this is process 1, process 2, process 3, process 4, and then back to process 1. Okay, so you see, this is how the direct current generator works. How it produces direct current. All right, so anybody have any question about this direct current generator? Okay, thank you very much for responding. Thank you very much. Okay, hopefully everybody else also no problem lah, because I see always the same few person that respond. Hope everybody else is listening also. Okay, although got recording, but please try your best lah, okay, to follow. Please don't feel complacent lah. You feel that, oh, got recording, never mind lah, don't want to listen. Later on I watch back. I tell you, if you don't listen now, later on you are not going to watch back lah. Okay, I don't think so lah. Okay, so okay, so let's continue. If no problem, then let's continue. Okay, so this is how the direct current generator works. Now, continue on, we want to look at alternating current generator. Okay, so like what the name say, alternating current generator generate alternating current. And like what the name say, alternating current is a current that flow in both direction, flow in two directions alternately. Okay, so you see the part that is different between alternating current generator and direct current generator is the commutator change into slip ring. Okay, the commutator change into slip ring, and then you see this ABCD coil, the coil ABCD, the AB side connect to one slip ring, and then the CD side connect to another slip ring. Okay, connect to another slip ring. So you have two slip rings. One slip ring connect to one side of the coil, another slip ring connect to the second to another side of the coil. Okay, you see or not? Okay, so the two slip ring also connect to carbon brush, and then connect to a load or here is the resistor. Okay, now, so let's look at how it works. Okay, let's look at how it works. Okay, same thing. Process 1. Let's say that this is A, B, C, D of the coil. It rotates in this direction. Okay, rotate in this direction. So same thing. When rotate like this, that means the coil AB and the CD is moving parallel with the to the magnetic flux. So that means no cutting of the magnetic flux. So zero EMF. Do not have any EMF induced. Okay, so you see here, okay, maybe not very clear. Let me make it bigger a bit. Okay, so you see here, This AB, this AB side is connected to the B slip ring. You see or not? Slip ring here labeled with A and B lah. So the AB side of the coil connect to the B slip ring, or okay, slip ring B. The CD side connect to slip ring A. You see this coil, this wire go here, pass through the slip ring B, go to the slip ring A. So CD connect to A, AB connect to B. Okay, can see Okay, now, so how it works? Okay, so here, no current, okay, no induced currents. So no induced EMF, so no current. Okay, but let's continue on to the process of no current. So that means from the graph, the graph is here, here, 0 volt. Okay, and then we go to process 2. Okay, when we go to process 2, the AB part of the coil is here. Okay, rotate until here, AB. So this side is CD. Okay, so remember just now the AB part of the coil is connected to the B slip ring. The CD part of the coil is connected to the A slip ring. Okay, now, so you see, if rotate in this direction, so that means the AB coil will cut downward, the CD will cut upwards. So by using Fleming right-hand rule, north to south, okay, the magnetic field like this, north to south, and then the direction of cutting is downward. So the direction of current is this direction. This is the direction of the current. So the current flow here, okay, maybe let me make it bigger a little bit so that is even more clearer. So you see the current flow this direction, flow in this direction, flow in this direction, go to the slip ring B, come out here, go here, go here, pass through the load, pass through the galvanometer. Okay, again, this one also got problem. You see, if the current is in this direction, so that means the pointer should be in this direction. Okay, pointer should be this direction because the pointer of galvanometer show the flow of the charge. Okay, so the current flow this direction, this direction, this direction, go to the slip ring A, and then from the slip ring A, flow to the CD. Okay, the coil CD, and then flow here, go here. Okay, like this. So you see the direction of the flow of the current. Okay, so here the direction will be in the positive side okay, is the positive direction. Okay, so this is the maximum EMF that can be produced because the direction of cutting is perpendicular. The direction of cutting is 90 degrees with the magnetic flux. Okay, direction of cutting is 90 degrees to the magnetic flux. Okay, so continue to the process 3. Okay, reach the process 3. So this side is A, B. This is C, D. All right. So again, if move like this, the direction of motion is parallel with the magnetic flux. So no cutting, so 0 EMF, 0 volt. The EMF will be 0 volt. So that means here. Okay, that means here. Continue to rotate. Okay, continue to rotate. Then we go to process 4. Then this side will be A, B, C, D. Okay, So you see the current flow from AB to CD. Okay, so this CD, the direction of current like this. Okay, so all right, so let's find out lah. Let's confirm the direction of the induced current by using Fleming right-hand rule lah. Okay, for the AB side. Okay, so this AB is going up, cutting upwards. The CD side is cutting downward lah. Okay, so the AB side cutting upwards using Fleming right-hand rule. Okay, direction of magnetic field from north to south. Okay, and then the direction of motion is upwards. So the direction of the current is going from A to B lah. Okay, that means the current is in this direction. So we'll flow this direction, this direction, this direction. Go to the slip ring A. Remember the coil CD, the CD part of the coil connect to the slip ring A. So it will come out here, go down here, pass through the galvanometer, pass through here. Again, problem with the direction of the pointer, it should be this direction. Okay. All right, so the current go this direction, go this direction, go this direction to the slip ring B, and then from the slip ring B, it will go to the coil AB. Okay, the AB part of the coil. So you see, this direction of the current is in the opposite direction as the process 2. You see or not? Okay, this is process 4. This is process 2. Okay, process 2 is to the left. Process 4 is to the right. You see or not? So in the opposite direction. So in the graph, we use positive, negative to represent the opposite direction lah. So in the opposite direction is to the negative side. Okay, this is positive, this is negative side lah. So negative to represent the opposite direction. Okay, can see or not? So this is process 1, this is process 2, this is process 3, and then process 4, the current is in the opposite direction. If continue to rotate, and then it will go back to process 1. Okay, it will go back to process 1, and the induced EMF will be 0 volt. Okay, the induced EMF is 0 volt. Okay, can see or not? 0 volt. Okay, so if we look at the angle of rotation, if we look at the angle of rotation, let's say that this is the starting, so 0 degree. This is 90 degree rotation. This is 180 degree rotation. This is 270 degree rotation. So this one, go back here, it will be 360 degree rotation. Okay, so here we can label, this is 0 degree. Here it would be 90 degree, 180 degree, 270 degree, 360 degree rotation. Okay, can see or not? So you see, because the direction of current that is induced is in 2 directions. When you rotate 1 round, 0 degree to 360 degree is 1 round. You rotate 1 round, the direction change 1 time, right now. Okay, from 1 direction change to another direction. So that means if it continue to rotate, the direction would change again, and then it would change again. So every time you rotate, the direction would change and change and change and change. So that means the current that is produced changes direction alternately change direction. So this is alternating current generator. Okay, this is alternating current generator. Okay or not? So this is how the alternating current generator works. Okay. So until here, anybody have any question? Okay, no question. Thank you very much. Thank you for responding. Okay, thank you very much for responding. Okay, so let's continue. Okay, let's continue. We want to look at the similarity and differences between direct current generator and alternating current generator. Okay, so the similarity, both also apply electromagnetic induction. Both the coil is rotated by an external force. Okay, coil cut magnetic flux, EMF is induced in the coil. And then what are the differences? The end of the coil are connected to a split ring commutator. This is for direct current generator. Alternating current generator, end of the coil are connected to two split ring. Direct current generator, the two sections of commutator exchange contact with carbon brush every half rotation. That means you rotate half. That means you rotate 180 degrees from one commutator will change to another commutator. That means the carbon brush, the same carbon brush will connect to a different commutator every 180 degrees of rotation. Okay, here the split ring are connected to the same carbon brush. That means no matter what is the angle it to rotate, the same carbon brush connect to the same split ring. For direct current generator, output is direct current. Alternating current generator, output is alternating current. Okay, so until here, any question? Okay, thank you very much. No question. Okay, so if no question, I got a little bit something to add. That is about the, you see the graph. You see the graph of the, you see the graph between the EMF, the magnitude of the EMF that is produced. You see it's a curve. Slowly increase, slowly decrease, slowly increase, decrease. It's a curve. So this one, alternating current generator, also the same. Slowly increase, decrease. So it's a curve. Okay, so why is it like that? Why is it slowly increase is a curve? The reason is the angle of the cutting is due to the angle of the cutting. You see, you see here. Just now we say that when it cut, when it move in this direction, this is 0 degree, right? Sorry, when it move in this direction, the direction of motion is parallel with the magnetic flux. Okay, parallel with the magnetic flux. This one, when it move downward, this one, the cutting is 90 degree. Okay, it's 90 degree. So 90 degree of cutting, then the 90 degree of cutting, then the EMF that is produced, it will be at the maximum. Okay, at the maximum. Okay, so let's see what happened in between. What happened in between, you see, when the coil AB is moved, it moved until here. Okay, it moved until here. Then the direction of the motion is this direction, right? Okay, it will be in this direction. So you see, during this direction, what is the direction of cutting? Okay, this is the magnetic flux. So you see the direction of cutting is at an angle. It is not 90 degree, you see or not? It is at an angle. So when cutting at an angle, okay, when cutting at an angle, the magnitude of the EMF is weaker. The smaller the nearer the angle is to 90 degree, the stronger the EMF. That means, for example, you see this angle is very small, near to zero right now. Okay, and then when the coil, if the coil is here, move until here already, then the direction of cutting is this direction. Okay, can see or not? Is in this direction. So you see, when in this direction, let's say this is the magnetic flux. So the cutting, the angle of cutting is this angle. You see, it's bigger. This one is 0 degree. The angle of cutting is 0. This one, the angle is bigger. This one is even more bigger. This one is already 90 degree. So the bigger the angle, the bigger the EMF. Okay, the EMF that is produced. So until at 90 degree, the magnitude of the EMF is at maximum. And when the angle is at 0, that means parallel. Zero angle, that means parallel. Then the magnitude of the induced EMF will be at 0. Okay, you see or not? So because when it rotate, the angle slowly increase, so it also cause the induced EMF slowly increase. Okay, slowly increase, and it produce a graph that is in the shape of a curve. Okay, it produce a graph in the shape of a curve. So it curve up, curve down, curve up, curve down, curve up, curve down. So this is very important because sometimes it can come out in objective question where it asks you to identify which is the correct graph lah. Okay, so it will give you like a graph that is curved and it's also graph that is straight line. So you need to identify the correct one lah. Okay. All right. Okay, so that is it lah about the electromagnetic induction. Okay, finish. Electromagnetic induction. So until here, any question? Anybody have any question? Okay, thank you very much for responding. So if no question, okay, so the objective question, as usual, you go and you try the objective question. Wait, let me see. Okay, go and try the objective question. All right. Okay, I want to discuss one exercise, one question. Let me see. Okay, so let's discuss question number 4. Is a structure question. Okay, question number 4, structure question. Okay, question number 4, structure question. Okay, so figure 5 show a bar magnet in the state of free fall into a solenoid. It is found that the galvanometer pointer was deflected when the bar magnet passes through the solenoid. Okay, so what is the physical quantity measured by galvanometer? Okay, so the physical quantity measured by galvanometer is quantity of charge flow. Okay, quantity of charge flow. That means how much charge pass through. Okay. D, explain why the galvanometer pointer was deflected. Okay, so the reason galvanometer pointer was deflected is, okay, you need to explain 2 marks. So what happened is when the magnet passed through the coil, the coil will cut the magnet, and then there will be induced EMF. So the induced EMF drive charge to flow in the coil. Okay, so because 2 marks only, so okay, so we explain as detailed as possible lah. Okay, as detailed as possible. Okay, so when magnet pass through solenoid cut magnetic flux of magnet, induce EMF is produced in solenoid. Induced EMF drive charge to flow in the solenoid. Okay lah? So this is the complete explanation lah. Okay, C, state one way to increase the deflection of galvanometer pointer. Okay, state one way to increase the deflection of galvanometer pointer. Explain your answer. Okay, so you see this is a solenoid. So there are 3 ways that we can increase the deflection. That means if we want to increase the deflection, that means we want to increase the EMF. So how to increase the EMF? There are 3 ways. We can increase the number of coil, we can use a stronger current, or we can cut the magnetic flux with higher speed. So if we want to cut the magnetic flux with higher speed, we can say that we drop the magnet from a higher, from a greater height. Because if you drop from greater height, then it will move faster lah. Okay, that is one way. Remember, when we want to give answer to this kind of question, we must follow the situation. The method to increase the current must be suitable to the situation in the question. Okay, it must be suitable to the situation in the question. This method of answering question should be applied to any other question, if any other topic. Don't care what topic is it. When you want to answer question, you must give answer that is matching or suitable for the situation that is described in the question. You cannot like just give a very general answer. Okay, sometimes can accept, sometimes cannot accept, but the best answer is you give answer that is matching or suitable to the situation in the question. Okay, so state one way to increase the deflection of galvanometer. This one, it says state of free fall. State of free fall. Wait. Okay, sorry, continue. Okay, so I give you answer for all three methods of increasing the current. Okay, so the first is we can say that we drop magnet from greater height. Okay, drop magnet from greater height. This is one. Or we can say that we use stronger magnet, or we can say that we increase number of coil of solenoid, like that. Okay, so this part is the part where we give suggestion on how to increase the induced current, okay, or induced EMF . And then we need to explain, so we need to give explanation for each method . So drop magnet from greater height, solenoid cut magnetic flux at greater speed. For this one, stronger magnet, we say increase rate of cutting of magnetic flux. Okay, increase number of coil. Also we say increase rate of cutting of magnetic flux. Okay, So these are the explanation for each different ways lah to increase the induced EMF. Okay, next. D, what happened to the galvanometer pointer if bar magnets stay inside solenoid? So, of course, the galvanometer pointer does not deflect lah. Okay. Pointer does not deflect. Or you can also say that it does not move lah. So, explain your answer why. Okay, no relative motion between coil and magnetic flux. Okay, like that lah. No relative motion between coil and magnetic flux. Or you can also say no cutting of magnetic flux by the coil of solenoid. Okay, also like that. Or no cutting of magnetic flux by solenoid also can. Okay, no problem. Okay, so until here, any question? Oh. Okay, if no question, okay, no question. I say that our time is until 12 o'clock lah. Okay, 12 o'clock, we have like around 15 minutes. Okay, okay, we do not have a lot of time lah, but I think we make good use of our time lah. Okay, we make good use of our time. We don't want to waste time because I want to finish up everything in this week lah. Okay, in this week, so that next week maybe you can do other revision and things like that. Okay, don't want to take up too much of your time also. So we make good use of the time lah. We don't want to waste any time. Okay, so so the electromagnetic induction we finish until here. Make sure you go and try all the objective question. Okay, now we continue on to the next topic, which is transformer. Okay, continue on to the next topic, transformer. Okay, 15 minutes also we can cover a little bit lah. Okay, I know maybe you are tired. Okay, but make good use of the time lah. Okay, so everybody can see the presentation. If you got problem, please let me know. All right, so we continue on to transformer. Okay, transformer actually is not a very long topic lah. Okay, so let's see. Okay, so first we need to understand how the transformer works. Okay, transformer, last time you already got learned about transformer in lower form science. We know that the transformer, the function of the transformer is to increase or to decrease the voltage of alternating current. Okay, increase or decrease the voltage of alternating current. Okay, so how does it work? This is what we want to learn here. How is it that the transformer can increase or decrease the voltage of alternating current? Okay, so we look at the structure of the transformer. Okay, let's say this is the transformer. Okay, and then here we got coil. Okay, we got coil. And then here also got coil. Okay, now, so this piece of conductor, this piece of metal is what we call the core of transformer. Or we call the transformer core, okay, transformer core. So usually the transformer core is made from soft iron. So that's why we call it the soft iron core. Okay, we call it the soft iron core because it's made from soft iron. Or if it's made from iron, then we just call it iron core. Okay, now, so on the iron core, on the soft iron core, so we have two coils. Okay, here got coil, here also got coil. So one coil is called the primary coil, and another coil is called the secondary coil. So how do we identify which one is primary coil, which one is secondary coil? So we need to look at which coil is connected to the power supply. So for example, if this one is connected to the alternating current power supply, then this coil is the primary coil. If this coil is connected to output, so for example, about here, then this coil is the secondary coil. Okay, so this is primary coil, this is the secondary coil. Okay, now, so how does it work? You see, the coil in the primary coil and the coil of the secondary coil, they are not directly connected. That means the current that flow in the primary coil, it doesn't directly flow to the secondary coil. Both of them are not connected. That means the circuit in the primary coil and the circuit in the secondary coil, they are separated. So the circuit in the primary coil, we call it the primary circuit. The circuit in the secondary coil, of course, the secondary circuit. Sometimes we also call it the output circuit. Okay, the output circuit. This one is the input circuit. Sometimes there are a lot of different names that we can give. Okay, but they refer to the same thing. Okay, now, so how is it that the electric current or the electrical energy from the primary coil can go to the secondary coil? Okay, so you see, when we turn on the alternating current supply, current will flow in the primary coil. So when got current flow in the primary coil, that means it will produce magnetic flux, right? Okay, it will produce magnetic flux. So the magnetic flux will flow in one direction. Remember, this is alternating current supply. So that means the magnetic flux will change direction. That means the alternating current will change direction. When the current change direction, of course, okay, some people say that don't have the 2.3, but I remember if you have the 4.2, the 4.2 and 4.3 is together, right? Okay, the 4.2 and 4.3 is together. 4.2 only. This is weird lah, because the 4.2 and 4.3 is actually photostated together lah. So everybody also 4.2 only and 4.3 only. Sorry. 4.2 only and don't have 4.3. Oh, I see. Anybody got 4.3? Nobody got 4.3. Oh my god. So problem with photostating. I think problem with photostating. I remember I sent together 4.2, 4.3 sent together because I photostate 4.1. 4.1, and then after that 4.2, 4.3 together like that. Oh, okay. If like that, I upload the note into the group lah. Okay, I upload the note to the group. But later. Okay, let me finish. Let me explain. Okay, you listen first lah. Okay, sorry you listen first Okay, you listen first. Then later I upload the soft copy. So maybe you can print out or something like that. Okay. Okay. So okay, let's continue first. Okay, so you see when the alternating current change direction, so what happened is the direction of the magnetic flux also change direction, right or not? The direction of magnetic flux also change direction. So every time the alternating current change direction, the magnetic flux also change direction. And you see the magnetic flux will be connected to the secondary coil through the soft iron core. So what happened is the secondary coil is exposed to changing magnetic flux. So this is a changing magnetic flux. If you still remember, just now when we talk about electromagnetic induction, there are two ways that we can induce EMF in electromagnetic induction. First is through relative motion. Second is when the conductor is exposed to changing magnetic flux. This is what we are talking about. When the magnetic flux keep on changing direction here, that means the secondary coil is exposed to a changing magnetic flux. And inside the secondary coil, you will have induced EMF inside the secondary coil. Understand? So that means now the secondary coil will have induced EMF. And the induced EMF will push the charge to flow. And the charge will, then that means in the secondary coil, you have induced current. You see or not? This is how the electrical energy can transfer from the primary coil to the secondary coil. Okay? Okay, now. So now that so the induced EMF in the secondary coil will also be alternating current. Okay, the induced current in the secondary coil will also be alternating current because the magnetic flux keep on changing direction. If the magnetic flux keep on changing direction, so that means the direction of the induced EMF also keep on changing direction in the secondary coil. So the current in the secondary coil also alternating current. And the frequency of both sides will be the same lah. The frequency of the alternating current here is 50 Hertz. Then the frequency in the secondary coil also 50 Hertz. Okay, get the idea. Okay, now that we know how is it that the electrical energy can transfer from the primary coil to the secondary coil, now we want to see how is it that the voltage can be increased or decreased. It's very simple. Previously, we all in topic 4.2, we also learned that, okay, for solenoid, how is it that we can increase the induced EMF? By increasing the number of coil, right? So this is the concept that we use here lah. If we want to increase the EMF or we increase the voltage in the secondary coil, what we do is we increase the number of coil in the secondary coil. So if the secondary coil have more number of coil than the primary coil, then the voltage can be increased. Okay, so the increase in voltage, the ratio is the same as the ratio of the number of coil. So let's say the number of coil is, the number of coil in primary coil is NP, number of coil in the secondary coil is NS. So the ratio between NP to NS, the ratio will be the same as the voltage. That means the voltage in the primary coil and the voltage in the secondary coil, the ratio will also be the same. So this means that if the primary voltage, let's say, is 10 volt, and the number of coil in the primary coil is, let's say, 50 ton, and the number of coil in the secondary coil is 100 ton or 100 coil, then what will happen is the voltage will become 20 volt. You see or not? So if the ratio is 1 to 2, then the voltage ratio also 1 to 2. Same thing. Okay, so this is how the transformer works lah. Okay, this is how the transformer works to increase or decrease the voltage. Okay, so of course, if we want to decrease the voltage, all we need to do is the number of coil in the secondary coil, we just make it lower than the primary coil. Then the voltage can be decreased. Okay, understand? Very simple. Okay, very simple, very easy to understand. Okay, okay, now, so we can have the equation to relate the primary voltage, secondary voltage, primary coil, number of primary coil, and number of secondary coil with this equation, with this simple equation. So that means if we know 3 of them, we can find the 4th one. Okay, you understand? Okay, okay, last thing, one last thing before we end for today's class is that, you see, why is it that only can use alternating current? Because only alternating current can produce changing magnetic flux, right? When the alternating current change direction, the magnetic flux will also change direction. Then only can induce EMF in the secondary coil. You imagine if you use direct current in the power supply, then that means the current only flow in one direction only. If the current flow in one direction only, that means the direction of magnetic flux does not change. The direction of magnetic flux is always in one direction only. So if that is the case, then there will be no induced EMF in the secondary coil. So in the secondary coil, there will be no induced current. Then the transformer cannot function. You see or not? Okay, so this is the reason why the transformer can only function with alternating current power supply. All right, so until here, any question? Okay, thank you very much for responding. Okay, so, okay, thank you very much for responding. So today, we only cover until here lah. Tomorrow, same time, 9 to 12, we will continue. Okay, we will continue with the transformer, and I believe we can finish up the transformer because transformer is not a very long topic. Also, we can finish up the transformer and continue to the chapter 5 lah. Okay, so hopefully until Friday we can finish up all the topic lah. All right, so later on I will send the note for 4.3 lah in our group, so you can go and download. And also the video lah, I have to wait for the Google to finish to produce the video out, then I can upload lah, and then you all can go and watch again lah if you want. Okay, so if no question, then thank you very much. I will see you tomorrow. Hopefully tomorrow everybody also can come lah. Thank you.
Thank you, sir.
Thank you, sir.
Sir.
Sir?
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 Sir.